All right, hi everyone, welcome back. Hope you all had a nice weekend. That was pretty fun. I went to Epic, the theme park. That was pretty cool.
You went to Epic?
Yes.
Is the food as good as they
What was
say?
your favorite section?
What?
What's your favorite section?
Oh. Well, my favorite ride was Stardust Racers in the middle, the roller coaster. The roller coaster was pretty fun.
Okay, bro. Okay.
Yeah. Anyway, system software. The final is Wednesday, and today is the final review day. So this podium, kind of weird. But yeah, so today is just a day for any kinds of questions you have. We'll review them, and I have a list of topics we're going to go over. Consider this as like a superset of what might be on the exam. Not necessarily everything that we're going to go over today will be on the exam, but all of this is fair game. And as always, you should be reviewing the homeworks and the projects as well. So just a reminder about the exam's format. Well, we got date and time. Again, Wednesday, regular class time. Come physically, bring your ID. You'll have to present that in order to receive credit. The breakdown is here. The kinds of questions you're going to be asked. And of the multiple choice, 10 will be from the first half of the course, 16 will be from the second half of the course. Okay, any questions before we start going through the topics? How is the cogen projects? How are they going?
Not too bad.
Okay, so reminder, I'll point this out as well.
I did encounter the type error that you pointed out last class.
So I'm glad I brought that up. Yeah.
That was definitely helpful.
Yep. I didn't know if it was going to be that common of an issue, but yeah, implicit typecasting in C and C++ can cause you to have overflow leading to infinite loops. One student had that issue last semester and came to office hours very upset. He wasn't very upset. He was very annoyed though, and I could see his code. He had written all sorts of comments and test cases to try and figure out why he was having this infinite loop. So I'm glad that helped you resolve that problem.
I still spent too much time on it.
Yeah.
I started getting very large negative values. I couldn't figure it out.
Yeah, there's your hint.
Rage quit and re-download the repo a couple of times.
So reminder, the Cogen 2 project is due tonight. Cogen 3 is due next lecture after the final. Just because of how little time we have this semester, I had to schedule the due dates to be sort of back to back like this. So yeah, make sure you're working on it diligently. I don't know, who has completed Cogen 2 by now? Okay, that's good. More than I had feared. Good. Okay, cool. Oh, I got an email. We'll see what that is later. Here we were, final review, there. All right, so start with the review. What makes the Unix file system hierarchical? Yeah?
Directories are a class of file, so in effect we have the, not necessarily like the physical memory, but files contained within other files.
Yes. So directories are also files. Directories map file names to what? What's the internal representation or identification of a file? What is that like?
Contiguous disk space.
Well, that's what a file is, but what is the operating system? Inode numbers, exactly. So each directory maps file names to their inode numbers. So if we have directories containing mappings for other directories, then you have a hierarchical ladder structure, a tree-like structure. I would draw an illustration, but I don't want to spend too much time on the first half material since the second half is where most of the questions are going to be. But if anyone wants to see more details on anything, please ask and I'll stop. I think we have plenty of time. So
So in a sentence, how would you say that? That what makes it hierarchical?
the fact that directories can have other directories as their children.
Like
Directories can.
folder structure?
Yes. What is the difference between absolute and relative paths?
Absolute path goes from the root, so it starts with a slash, and relative path goes from current working directory.
Yes, exactly. So if the directory path, if the path, a file path, begins with a forward slash, you immediately know you have an absolute directory, an absolute path, I should say, absolute path. Whereas if there is no leading forward slash, then the path is relative to the current working directory. How are parent directories referenced in the file system?
Dot dot.
Dot dot. So the special character dot dot. Actually, maybe I'll show something here. I'm re-implementing the class project all in C because I want to make sure next semester that nobody has questions about C++, so I'm trying to do it all in C. And this is actually a good example here. We can see this is like a whole file tree of the directories containing other directories. The dot is the current working directory. If I were to take a path here, stat makefile, you can see that's the absolute path to this file. And the path ./makefile also works for referring to that file. I can run the stat command, pass the relative path ./makefile, and that also works for accessing that file. There's a fly on my glasses. Okay, yeah. We received a similar question on the midterm as to this question. Given a tree, which file is being referenced by a given path, you might be asked another question like that in the final. So be prepared to be given a file tree and be asked to maybe do some actions to manipulate that file tree using both relative and absolute paths. In drawing a tree, I'm not going to ask you to draw anything, but I may ask you to interpret a drawing, so be prepared. Okay, what is the working directory and how do you display it?
Where you're operating from, you can display with PWD.
Yeah, PWD. Yeah, that's what you were going to say. How do you change the current working directory? Yeah, CD. And why? So is CD a program or a shell built in? Why is it a shell built in? Why does it have to be a shell built in? Anyone answer that? This may be a more deeper knowledge question, but why does it have to be a shell built in?
Because the current working directory is stored as like a variable kept by the shell.
Yes, exactly. So the current working directory is where the shell is currently operating from, so it has to be internal to the shell. So if you're going to execute another program, it won't be able to change the value of a variable inside bash. So the built-in is built into bash. Yeah.
So for this, will we be able to make a bunch of notes like we did for the midterm?
Yes, you get 12 pages. 12 pages, double-sided notes. You can actually check out, I'll point this out now since you asked. There's actually a link right here on the home page for the final itself, and this should be up to date. I just updated this a few minutes ago. This is what has more information on the final exam itself. Yeah. What is the Unix standard command to rename a file? Move. Yeah. MV. What is tab completion?
My favorite thing.
Yeah, it should be all of your favorite thing, hopefully. Hopefully you're all using it by this point. So what is tab completion?
Completes your command or guesses.
Yeah.
Guess what you want to type.
Pressing tab to automatically complete the rest of your command, or presenting all the other options if the prefix of what you typed so far has multiple matching suffixes or suffixes. I never know what the plural of suffix is. What Unix standard command, I need to fix that typo, will show you the text of a file? Cat. Yeah, what is cat short for? Concatenate. What does grep do? A pattern. Normally mostly we've been searching for strings, but you can use grep to search for a pattern as well. How do you change the working directory to your home directory?
CD tilde.
CD tilde, what's another way? Maybe, you don't need to know this, but what's another way?
CD $,
Yeah, CD dollar sign all caps home. So that's the shell variable containing your home directory. So, bless you. If I say echo home, you can see my home directory is /home/bpapis. I will recommend, you don't need to know this with the final, but if you're writing your own bash scripts, I recommend using $home, not tilde, because tilde is something special recognized by the shell. $home will be expanded by the shell before being passed to any other programs. So in shell scripts, it's usually better to use $home rather than using tilde all the time. But for convenience, when you're typing in the terminal yourself, you can just use the tilde. What is the Unix standard command to delete a file? rm. If you use rm, will it immediately delete the file from the disk? No. When does deletion from a disk actually happen?
When it gets overwritten.
When are the bytes of a file made available to be overwritten? When a single path to the file is deleted or removed, or
The last.
Every hard link to that file is also removed.
yes, precisely. Every hard link to the file has been removed. So internally, the operating system keeps track of all the references, the reference count, for a given inode number. And if you delete all the references to a file, all the paths to an inode number, then the file itself gets freed up and other programs, other processes are able to overwrite those bytes. So the bytes are not zeroed out or anything. They're still there. So you could perhaps find deleted files and recover them that way. Using bash, how do I redirect standard out in of a command?
Angle bracket.
Angle brackets. So if I wanted to redirect standard in, do I use less than or greater than? Less than. So I could say cat makefile, print out the contents of this makefile here. I could also say cat makefile, and then angle bracket like this, out.txt. And now out.txt has the contents of my makefile. If I wanted to redirect the standard out from one command to another, what do I use? A pipe, right? So a pipe is the easiest way to do that. So I could say cat makefile, pipe it to WC. What does WC do?
Gives you the word count.
Word count. So what does it print out exactly?
Words, bytes. I can't remember.
New lines. It's the last one.
New lines, or-
You can see it here. If I wanted to also pipe, you don't need to know this, but we had reviewed this in class briefly. If you want to also pipe standard error to their next command, what do you use? What operator? Here's a shorthand for this. Redirecting standard error as well.
Double bracket.
So we're still using pipes, not going to be double brackets. Ampersand, that's exactly it. You add an ampersand after the pipe. Now there's no example here because this file exists, but if I wanted to pipe standard error, I could also put an ampersand after the pipe to also redirect standard error to the next command. What does make do?
Files your program.
Yeah, well, it'll compiles your program as a specific application of make. What does it do more generally?
Builds your program.
Yeah, well, it runs some predefined, what do they call? Well, makefile is what you have, but what does a makefile consist of?
Yeah, it's stuff that you use in order to
Okay.
compile or reclaim your
What's the name of that? There's a specific name for these
prerequisites.
rules. Exactly, make rules. Each make rule has what? There's 3 components. It might be on the screen right now, I'm not sure.
Prerequisite, target, recipe.
Yes, exactly. So, well, if I run a command like make clean in my directory that I'm in here, what by convention should this command do?
Remove binaries.
Remove compile binaries. So if I run this here, it removes all the files in my bin directory and my object directory, which I've placed in this project for placing compiled object files and executable binaries. If I wanted to add a clean rule to a makefile, how should that clean rule work? What should it? What flag should I add to RM, for instance? dash F, so I need force, because the files I'm trying to remove may not exist. I want to make sure it always works. What should I add the clean rule to the list of in order to ensure that clean works even if there's a file named clean in my current directory? Phony, add it to the .phony rule. So here I think I've done that. If not, I can fix my file right now. Yeah, right here. I have a clean rule in my .phony list. This is to ensure that if a file named clean exists in my current directory, running make clean actually still runs clean. It doesn't just leave it there. All right, we can skip this one. All right, version control. So what git command copies commits from the local repo to the remote? Push. Yeah, git push. What git command copies commits from the remote repository to the local, assuming the local one already exists? Pull. What if the local does not already exist? Clone. Yeah. What command stages a file? Git add. What command creates a log of the change to a staged file to the local repository? Commit. Yeah.
You were
Go
trying
on.
really hard not to use the word, huh?
The what?
You were trying really hard to use every word except the word, huh?
Yeah, yeah. Sometimes it's challenging. If I want to access the manual for a syscall, what command should I use? And what if there is another command that shares the same name as the syscall? Man, yeah. And then how do I specify, let's say I open man open, and this brings up the manual pages section 1 for the open command, but I want to open up a different section.
Specify the page number or section number.
Exactly, so man 2 open, and then I get section number 2 for the system call open, as opposed to the command open. So you can always check man, you see the list of all the different sections in the manual pages, and see what they all reference. Using the open syscall, yeah, use the open syscall to open a path given in the string char star file path variable. So I'll do this quickly. Okay, I'll just say const char star file path. I'll just leave it uninitialized, or initialize it to a directory here, just the current working directory. What flags do I need to pass if I just want to open the directory for reading? Maybe what I'll do actually here is, this file is called test.c. Maybe what I'll do instead is make the file open itself for reading. Kind of meta. So read only, that works. How do I check if open succeeds or fails? Yeah, so I'm gonna press number 2 and then capital K here in Vim to open the man pages for open. Look at the return value. It says on error, -1 is returned, and error now is set to indicate the error. So to check if open succeeds, I can just say if -1 is equal to FD, then I know that I failed. P error, exactly to print the error number. What's by convention should be passed to P error? The name of the syscall that failed. And then we can exit with exit failure, which should just be 1, some non-zero value to signify failure. And I think we need unistud for open? No, file control. And standard IO. I think we do still need standard lib for exit. Yeah, we do. Oops. Okay. There we go. Alphabetized. All right, and then after we open a file, what syscall should we use to I don't want to say the word, but what syscall should we always call after we're done with our file after we've opened it? Close, right? I'll skip error checking here because if close fails, then there's not really much we can do anyway, so I'll just leave it here as this is. Let's try running this. So we can say gcc test.c. All right, I got some kind of typo here. Okay, and it seems like close is not defined, so we need to get the correct header for that. It's in unistud. All right, here we go. Yep, no errors. We have a.out. I'll run that, and it does nothing because we haven't printed anything. So seems like it's working though, and I can test this by echoing out the exit code, return 0. So it seems to work. I'll return 0 explicitly here, but the C standard actually says that for main specifically, you can omit return 0, and that will be the default return value for main if no other error occurs. All right, we've checked this. We've reviewed this. How do you check for and terminate the program on an error with opening a file? You check the return value for being -1. Use the read system call to open the first 200 bytes of a file and print it to standard out. So what do we need for the read system call? What 3 arguments does read accept? Does anyone remember? Exactly. So we need the file descriptor, the buffer we're reading into, and the number of bytes that we're going to be reading into that buffer. So I'll declare a char array here, char star buff, size 200 we'll say. Call read, fd, buff 200. And we'll just check if -1 is equal to that, then we'll emit another error. Let's just make sure we got it right. So size t is the return type, return value. On error, -1 is returned. And let's print the value of the contents of the buffer afterwards. Will the contents of the buffer be null terminated? No. So is it safe for me to try and print the contents of the buffer like this? No, because there is no null terminator. So what do I have to do instead? Yes. Unfortunately, I have to go character by character and print each individual character. So there's a faster way to do this, or a slicker way with a format specifier, but I'm not going to do that. Okay. Oh. What's the error here? What's the reason why I got this compilation error? Is it what? Yes, exactly. I accidentally declared an array of pointers, not an array of characters. Because this here actually currently will declare an array of 200 char pointers. So I'll delete that, try this again, and now it seems to work. And if I print it out, you can see the first 200 characters of the file itself, test.c. Okay, this isn't on here. What if I wanted to create a file instead? Yeah. Oh, yeah.
Couldn't you just like make the buffer like 201 and then set the last one to be like a null?
You could. That's another idea. So yeah, what your classmate suggested is that we make this buffer 201, or alternatively, we only read 199 bytes. and then we can just set manually buffer 199 to be equal to percent or 0. Actually, this should be 190. No, I think this is fine.
If you
199.
don't have that many characters in the file that you're reading, you're still gonna, like, when you go to print it, you're still gonna put, like, the whatever garbage data was in there, right, up until it hits that number
Yes,
on there?
yes, exactly. So I'll just set this to the null terminator here. And now we can actually, should be able to print the buffer contents directly, because with the null terminator, it's safe to pass it to printf with the %s format specifier. So I think this should work if I can just remember the semicolon. And there we go. That seems to be correct. We have one less character than last time, one fewer character printed than last time. Last time we had that last parentheses here, opening parentheses, but now we don't because we're saving that, overwriting that one character with a null terminator. And yes, oh yeah, question.
Read if it doesn't return -1 because of an error, it returns number of bytes read, right?
Yes, read returns -1 on error, otherwise it returns the number of bytes read. So if we looked at the return value, on success the number of bytes read is returned, on error -1 is returned. However, the number of bytes read can be less than the number of bytes you requested. Why could that be? It says it here, but
The file.
What?
There's not that many bytes in the file.
not that many bytes in the file. What's another reason? That might be a problem. I'm not actually sure. It's probably a problem. Yeah.
Maybe your buffer's not big enough?
No, you'll get an overread error. You'll get an overread if the buffer's not big enough. But that won't be necessarily an error. What could an overread do?
Segfault?
Segfault, or what could it also be used to do?
Stack smashing?
Smash the stack. Another way in which read can be interrupted is through a signal. So a signal can be sent to your program while it's in the middle of reading, if it's reading a large number of bytes, and then it would have to be resumed later. So there's ways to wrap calls to read in loops to ensure that even if read is interrupted, you keep reading until the file is totally read into the buffer. There's some examples in the class website on that. You don't have to know it for the exam, but just to be clear, there are multiple ways in which read can be interrupted, and it's in general not safe if you're writing like production code in C to just call read directly and assume that it won't work in one try. And yes, you can use create to open a file if you wanted to. And we'll skip the reading here. What am I missing? When we create a file, what do we need to pass in?
0644.
Sure, what is 0644 specifically though?
Permission.
The permission bits. So we don't need to pass necessarily 0644, but this is just a shorthand we've commonly been using for permission bits. I won't go into exactly what it means. It'll probably be easier if I just run the program and then show you what it means. So gcc test.c a.out prints nothing because we were printing the buffer, which is empty. And let's see. So if I were to say stat out.txt, you can see these permission bits here, 0644, correspond to read, write, read, and read. So read, write for the user, read for the group, and read for others is what these permission bits specify. Some trivia. I was reading a book on operating systems today, and I found a historical note that Ken Thompson, one of the fellows who invented Unix, said that if he could go back and change Unix in some way, one of the things he would do, the first answer he gave actually, is that he would change create to be spelled with an E. So. All right. So enough of that. What's this call can you use to find the size, number of hard links, other metadata about a file? The stat syscall. Does stat return this value in its return value, or how do we get it? Pass by reference, exactly. So we pass a pointer, well, pass by reference, yeah, to the stat syscall. So right here you can see we pass this stat struct to the stat syscall, which will be populated with the information about the file that was passed to it, if stat succeeds. What syscall can you use to find the name of a file?
Find?
Is find a syscall?
Oh, no.
Maybe this is slightly of an incorrect question. Reader, yeah. And this makes this question kind of wrong because reader is in manual page section 3, which is for library functions, not system calls. So I should fix this question, but yeah. Write a code snippet that will print all files in a given directory except for the dot and dot dot. We don't need to write the code, but conceptually you all should be familiar with this hopefully by now. What 3 syscalls would you want to use with directories in order to do this?
Open, read, and close dir.
Yeah, opendir, readdir, closedir. How do you walk a directory using readdir? It's like a linked list, right? Yeah, you can use a while loop. While the result of readdir is not null, keep walking the list. There are syscalls for opening and navigating directories, but they're a lot lower level than other syscalls we're using in this course, and they're kind of a pain to work with, so we use the library calls for those instead. All right, write some C code that uses Unix standard syscalls to create a new process that runs the ls command. So let's delete this, or I'll delete the contents of here at least. First of all, creating a new process, what syscall do we use for that?
Fork.
Okay, I'm going to use the switch fork idiom we've seen in class before here. What does syscall return? What does fork return on error?
Negative 1.
-1. I'll just exit 1 here for failure. When does fork return 0?
In the child.
In the child process, so I'll put a comment here for now. What does fork return in the parent?
PID of the child.
Exactly, the PID of the child. So this question's asking us to create a new process that runs the ls command. Okay, so what syscall do we use? Actually here, how do we pause the parent process until the child process is done running? Wait, right? And I'm going to pass null here. What is the argument to wait?
What's a pointer?
A pointer to what? So it's a pointer to a wait status, well, an integer that's supposed to store the wait status, the status of the process that terminated. So there's all information you can get from this. MM pages describe it. But basically, if you just leave this as null, you tell wait that you don't care about recording the status of how the child process exited. Okay, so now in the child, what's this call we're going to use to execute ls? Exec, and which kind of exec do we want to use? We'll use VP. So if we use VP, what does the V mean? Variable. So we need to pass what is a variable?
The arguments.
The arguments to ls is a variable. So I think we can pass them directly in line here, like so. We'll pass no arguments to ls. We'll just say ls null.
I don't think you even need the curly brackets.
Uh,
I think you can do without them.
if we omit the curly braces, what version of ls should we use instead?
Oh.
Or exec, I should say. Sorry, exec. LP. So if we omit the curly braces, we need to use exec LP. With the curly braces, we have to use VP. And what does the P in exec VP mean? Path, which means what? What does it allow us to skip doing?
Listing out like exactly where LS is like originating from.
Yes, so we don't need to specify the whole path to ls. Instead, exec will first look in our path variable, environment variable, to find any programs named ls and then run those when it finds them. Should ls return? Does it return? What does it return?
You mean that?
Exec, sorry, exec.
Should it?
It should not return. So exec does what? It replaces the processes running program with another program. And so if exec returns, that means that it failed. So we don't have to check if exec's return value is -1. We can just simply say exit 1. And I won't ask why, but just remember that from child processes, we typically use _exit as opposed to regular exit. Let's try compiling this. So we might need to declare this in a separate variable. Arg_v is here. I think this should be like that. Implicit declaration of weight. I think weight is included in sys/weight.h. Yeah, there we go. A.out, and it seems to work. Verify it works. We can just echo out the return code, and it's 0. So yes, it seems like it's working. Okay, write code that creates a new process where the original writes parent and the child writes child, both to standard out. Pretty similar to what we've already done here. You would just change out exec with calls to printf. Write code that replaces the current process with the stat_ls command. We would just not use fork. We would just call ls directly, or call exec directly in the parent process. Write a program that opens a pipe and reads to and writes from it. So do we remember how pipes work, how to create pipes and interact with them?
You would like put pipes and you would like close the read end of the pipe for the, all depends on what you're trying to do here. You close the read end for the child.
So let's assume we want the child to write to the read end of the pipe. Or, I'm sorry, we want the child to write to the pipe and the parent to read from it. So
you close the read end for the child and then close the write end for the parent and then you would yes.
Okay, so let's step through this. There's a lot of steps here for opening pipes. So what do we first need for the pipe syscall? What do we need to pass to the pipe syscall? The what?
Or file descriptors.
Yes. How big is the array? 2. So we'll say fds, fds 2, and then fds. I'll skip some error checking here. Normally you should have it, but I'll skip it for now. Let me call fork, and we'll assume that the child writes and the parent reads. All right, and I'll change this out for exec LP. Let's say we want to, for this example, let's just say we're trying to do ls to wc. I think we've seen this before, pretty simple example. That's why I like to show it. What syscall, so we're going to be redirecting the out of the child to the right end of the pipe. First of all, 0 refers to what, and index 1 refers to what in the pipe. Index 0 is the read end, and right end. I think we can click on the pipe or open up the pipe and pages here and see this. So pipe FD0 refers to the read end of the pipe. Pipe FD1 refers to the right end of the pipe. Okay, so in the child, we want to redirect the standard out of the child to the right end of the pipe. So how can we redirect the output of a C program to another open file descriptor? Dupe2, right? So dupe2, what comes first to dupe2? FDS1, yep. And then what should be the second argument?
Standard in file name.
Standard in or
It's writing standard out.
standard out, because the child is writing, we'll say. Does the child use the read end of the pipe? No, so we can just close that. And after successfully duplicating the file descriptor for the right end, do we need that file descriptor anymore either? No, so we can close that as well. Now meanwhile in the parent, what do we have to do? What should we do in the parent? How is this? It's going to be similar to the above, but what should we do instead?
Kind of the opposite. Yeah, it goes to our head.
Yeah, so we flip it around. So the parent is reading, so we can close the right end of the pipe first. Then we can use dupe as well here. FDS0 and standard in file node to redirect standard in to the read end of the pipe. And then finally, what do we have to do in the parent if we want to simulate this pipeline here? So we have to use exec and exec the WC command. So we'll copy this here. I'll actually change this out for, gotta fix this actually. There we go, that should be good. Okay, I think that might work. Let's see if it does. Okay, and there we go. That seems to be correct. Let's try it out. And yeah, we have the same output running the pipeline directly as we do from running our compiled binary. It seems like this switch fork is working. All right, any questions? Okay. This one should be easy. We've already reviewed dupe2, so kind of is subsumed by this example. Internally, what is dupe2 doing? It's achieving redirection, but how does it do this inside the file system itself, or the yeah?
The next available place in the
So that's dupe1 chooses the next slowest file descriptor. What does dupe2 do?
Doesn't it close the second argument and redirect to the first one?
So it closes the second one, and then it reopens it. And what does it do when it reopens the second argument? Yeah.
It'll point it to whatever the file descriptor is pointing at.
Yes, exactly. So it reopens the second argument after closing it, and then reopens it to point to the same description, the same entry in the open file table as the first argument points to. That's how redirection is achieved. Okay, any questions on the first half material? Kind of blew through that faster, but that's because, again, only 10 of these questions are on it, and I'm not going to give you any super hard trick questions for the first half of the material. All right, so let's take a break until 4:50, and I'm going to take attendance now. Okay, let's close that. And we're on to second half material. So this is fewer topics, but I think there's a lot to talk about here. So first, the stages of compilation, source to process. Be sure to know the order, all these phases, and the order in which they occur, which is the order listed here. Can anyone tell me, one person at a time, what each of these phases do? So starting with pre-processing, what does pre-processing do?
Checks to see if you have the right headers. Right?
It does something involving headers, yeah.
It fills in the headers with like the actual code.
Yeah, it expands the headers or replaces them with the contents of the files they're referred to. There are other things that pre-processing does. What are some other things the preprocessor does?
Inline
Inline what?
functions.
They're not functions, what are they called?
Macros.
Macros, yes. So the preprocessor inlines macros. There's also a third key feature of the preprocessor that you may not have seen in this class, but maybe you're familiar with. Does anyone know? What's the other so-called preprocessing directive that the preprocessor supports? You'll see this a lot in real-world C code. And what? No. No. It's hashtag something. So hashtag include for headers, hashtag define for macros, hashtag what for this third construct that I'm alluding to.
Is it if then?
Yes, hashtag if, hashtag if def, that's the construct. Since we're kind of ahead on time, if we finish a little early today, I'll show you some really nasty, kind of great tricks you can do with macros at the end of this lecture. The first 2 years of my PhD research was on macros. So I know a few things you can do with macros that are kind of cursed, but also really cool sometimes. Okay, compilation. What does the compilation phase proper actually do?
Turns your C code into an object file.
Close. We'll assume that the actual object file part is handled by another phase, but what does compilation turn your C code into then?
Into like a .s file, which is like the instructions in your instruction set as if they'd like been handwritten. If they're not in the binary code, but they're not in C.
Yes, they're using the mnemonics. So it compilation converts your high level source code into the lower level assembly code corresponding to your computer's instruction set. Modern compilers don't always translate, well, they often don't translate directly to assembly code, but they use what's called an intermediate representation, or an IR. I think I talked about this before. Does anyone know what the advantage of translating code to an intermediate representation is, rather than going directly to assembly code?
Different like systems, it's like they have slightly different things that you need to write in the assembly code.
Yes, well, that's true. So what does translating to an IR help us avoid doing? So let's say I have, I'll draw an illustration here. Let's say I have some compiled languages like C, Go, Rust. These 3 compiled languages, yeah?
If you were making like I don't know what you would need to do, but like, you wouldn't have to make one for each individual one. You would just make one and then you could use like the connecting language for all of them.
Exactly. So if I had 3 different operating systems here, target operating systems, Windows and Mac, which may actually be, sorry, it shouldn't be operating systems, it should be architectures. x86, Spark. I think PowerPC is another one, an older one. I think that's another example. Normally what I would need to do, if I were just compiling these source languages directly to an assembly, I would have to write a separate backend for my compiler So the backend is the part of the compiler that translates the code to the assembly representation, whereas the front end handles lexing and parsing. I would have to write a separate backend for each individual source to target translation. And as you can see, this is quickly becoming very messy with tons of lines everywhere. So instead, what researchers have thought to do, this is definitely one of like the biggest inventions I'd say in programming languages in the past like 10 years, is to create an intermediate representation, IR. Commonly, this is going to be LLVM-IR in practice. That's the name of the most commonly used intermediate representation. And this way, source languages only have to be translated to the IR, and then they can go from there to all the individual target languages. So now instead of having n times m number of lines, you just have to do n plus m number of translations, which is much more tenable, much more easier to maintain. Okay, so what does the assembly step do during compilation? Yeah, well, it doesn't turn it into assembly. It doesn't turn, what is it?
Well, no, the like text put into the grammar for the.
So what? Not quite. What does the assembler take as input, and what does it produce as output?
Essentially to
Two binary. What kind of what do we call these binary files? What?
the object file.
Object files, exactly. Can these object files be executed directly? Typically not. What do we need to do next? And linking is next, but what does linking actually do? Why do we need to do linking next in order to execute our object files?
It combines multiple object files so they can be executed in a
Yes.
single file.
Yes. What specifically does it? While combining them, what does it do that enables the programs to be made executable?
Something with symbols that we can find before.
Yes, exactly. It resolves references to symbols that are used in one object file but defined in another. So we saw this. There's two different ways of performing linking. There's dynamic and static linking. I won't go into too much detail here on that, but linking is essential for resolving references between object files. That's the big idea. So loading, what does loading finally do? What? Yeah, basically, just loads it into memory and sets it up to run. Sometimes the loader will also help resolve references to shared libraries when the program goes to run. And that's, I believe, why the linker is called LD, because sometimes the commands are sort of connected. But all you really need to know for this class is that the loader sets up the program to actually run. Puts it in memory and gets it ready to run. And it's not really part of compilation proper. These stages are really part of compilation. This is part of source to process, converting the program to a process that is actually running on your machine. Okay, arithmetic for simple IR. Let's write some example code here. Not sure if it'd be better to do a drawing or to just write some source code. All right, I'll just do a drawing here. So we'll say, how do I start a function in simple IR? Anyone remind me? How do I define a function? Yep. I'll just call it main. And then what comes after the name of the function?
You define your local variable, or you
local variables, we'll just declare two, x and y. And then what comes after local variables? Parameters. So we can just say, we'll say x and y are the parameters as well. And now if I want to add two variables together in a simple IR, so if I want to add the x and y together and store the result in x, how do I do that? X plus y. And then how do I end the function?
End function?
Yeah, I think at one point I erroneously said that it was end space function, but no, it's just one word, end function. So this is the, let me see if I can put a frame around this. Text in a container, app selection and frame, there we go. This is the simple IR code. What's the corresponding assembly code? Or at least for, maybe I'll be clear here, for x equals x plus y. Yeah.
So first, by convention, you'd move, for instance,
Well, let's focus on just, or are you just going to say x plus y? Or, okay.
or I was gonna say like move into Rx and Rbx, but the actual operation would be add. Presumably you would have.
So we use add, that's correct.
If we had already loaded, say, like x into Rax and y into Rbx, we could use add Rbx, Rax, and then load that output into.
Okay. What do we need in order to actually store the result back in x though?
Oh,
What do we need to know?
the offset,
The offset of x from what?
which is more than.
Or what is it the offset from?
From the base.
The base pointer, the base of the stack frame. So,
Starts at 16, right?
we'll just make a little table here, symbol and offset. So we'll say x, which you're right, it begins at offset negative 16. Why is it negative? The stack grows down. Yep. And we'll say y is at negative 24. With this symbol table, we can write some assembly code that actually translates x equals x plus y. So let's first move the value of x into a register. So what instruction do we use to move a value? MOV. And what comes first, the source or the destination? So how do we specify the source here? RBP. And then the destination? We'll use RAX. We can use any general purpose register, but the A register is the first one we've been using in our example, so we'll just use the A register. Now we should probably move the second argument as well into a register. So what should the offset be for y? 24. Second operand, I should say, not argument. Now how do we actually perform the addition? Add. Okay, and if we do this, then where's the result stored?
RBX.
RBX. And so how can we put the result back into the x variable? Move. What are you moving into?
RBX.
And we're moving into what?
Negative 16 RBP.
My 6 key sometimes does not work. Okay. So this example here, if I were to change this to multiply, what do we have to change? What's the one thing that has to change? What do we change the add mnemonic to? IMUL, integer multiply. If this was sub, what do we change? Sub. However, would this be, is there something else that we need to change here? Yes, the order of operations is important, so we have to change this to RAX in order to correctly subtract y from x and not x from y. So the right-hand side is going to be the destination always, so this becomes x equals x minus y. or really RAX equals RAX minus RBX. All right, now for the tricky one, the trickier one, division. So what do we have to do for division? Yeah.
So first we want to sign extend the numerator.
Okay.
So we use CQO RAX, or just run CQO to get it.
So do we have to move the value of the numerator into any register first?
A special
So what is that register?
RDX RAX.
So it's just RAX. So first we have to move the value we're going to be dividing by, RAX, or dividing RAX, into, and I'm sorry, the numerator, which is X, into the RAX register. Then we can run CQO, call CQO, to sign extend the A register with the D register, RAX, RDX. Then how do we actually perform the division? What's the instruction for division? IDiv, exactly. So imul, IDiv. And what do we pass as the single argument to IDiv? The RBX, which we'll have to move back in here to fix this, but we'll say move 24. More generally, this is the denominator. That's what we're specifying as the operand to IDiv. And then where's the result stored afterwards? RAX. So we can say move negative 16, or sorry, RAX into negative 16 RBP. If I were to change this to modulo, where's my percent sign? There it is. Then what do we have to change here?
Instead we move RDX into negative 16 RBP.
Yes. Yes. Oops. Not F, R. So with modulo, the remainder of division is always stored in RDX, so all we have to do is just change the move instruction to move out of RDX instead. Okay. I think that's good for arithmetic. Yeah, question?
CQO sign extends RBX, oh, sorry, RAX, right?
Yes. Yes, yes. Yeah, question?
That was a stupid question, but why did it start at 16 or negative 16?
It's not a stupid question. It's a good question to ask. The reason why is because what does the ABI specify that we first have to push onto the stack when we call any function? There's two registers we have to push onto the stack first, yeah.
The return address and the base pointer?
The base pointer, so the return address is already there. The base pointer we add next. And then what's the next one we add after that, according to the ABI? RBX. And I've kind of been lying to you all. The ABI specifies that you're supposed to push a lot more registers onto the stack as well to preserve them. But I'm not bothering with that. I just show you the one to give you the idea that there are some registers you have to push onto the stack according to the ABI. But there's like 6 of them you're supposed to preserve. But we're not touching them, so it doesn't matter anyway.
And why is that? Is that just so that when you return back to the original function, you still have those values?
Yes,
Okay.
that's why.
So you use them for both functions.
Yep, they're callee preserved. Yep. Yeah, question?
So for CTO, CTO sets the products and the remainder. Is there a way you can actually like change that, or is it just always gonna do that?
CQO always sets the numerator.
Yeah. The numerator and the remainder registers, right?
The remainder is going to be set by IDiv. IDiv is what actually puts the value, computes the division, and then stores their value in the A register and the D register. But you can't change what destination registers are going to have the result of the division afterwards. So you can't just, you can't just specify IDiv. Unfortunately, you can't do this. You have to manually extract it from the A register or D register afterward. Okay. Any more questions? Okay, so I don't think probably won't be walking through any stacks today, any stack diagrams, but I encourage you all to go back to the lecture videos. We have recordings. And go back to the diagrams and look at how we walked through this execution of the stacks if you're confused as to how that works. I think it really helps elucidate how the stack actually works, how these instructions manipulate the stack. All right, branching. So let's change this example a little bit. If x is less than y, go to end, and here we'll say x equals 1. I don't know. So for this example, let me make this a bit bigger. I'll delete this frame actually. I'll make the colors different so it's easier to see the difference. Okay. For these 3 lines of code here, let's try and translate them. So for branching, for conditional branching, what instructions do we need to emit?
Well, first move x and y into registers.
Okay, so we'll do that same as we done before. So move RBP into, we'll say RAX for the first operand. And now how do we actually perform the conditional branching? CMP, right? CMP, which one should come first?
RBX.
Yeah, I believe it's RBX that comes first. RBX, RAX, and then how do we actually perform the jump? What was it? JL for this example, because we're jumping on less than, and we're jumping to end. And then how do we actually translate the end label to assembly? It's the same thing, yeah. If I had how do we translate, I won't write this down, but what's the translation of the simple IR go-to statement to assembly? What is it? It's just JMP, yeah. So for go-to, I'll write it, I guess. For, let's say go to, I don't know, we'll just go back to end, infinite loop, go to end. This would just be JMP end. If I were to change this to another operation, another relational operator, the less than to greater than or equal to, what would the instruction here change to? JGE. So in general, just remember there are a variety of conditional jumping operators, or instructions I should say, that you should just be aware of. You can put them all in your notes. There's like a list of them, but the mnemonics are pretty easy to remember, I think, if you don't want to take notes on them.
And in between there, you would have the x equals 1.
Yeah, you're right. Sorry, I skipped that, but you're right. We would have move 1, -16, RBP, something like that. Yeah, but good catch. Okay, any questions about jumping or branching? All right. So remember, even though we don't have structured programming in simple IR, we can use branches to simulate loops and other control flow mechanisms. So this is how C code, when it's compiled down to assembly code, actually achieves looping, is through these sort of labels and jump instructions under the hood. Okay, pointers. Let's say x equals ampersand y. How do we translate a reference operation like this? I'm surprised no one else's phone is going off. Okay. Okay, so we're going to move the value. So first of all, we have to get the actual address at which the y variable resides at, and then we're just going to move that address directly into the destination variable. That's the big idea. Get the address of the variable we're referencing and store that address in the destination variable. So if we're getting the address of the y variable, how should we, well, I think you just said it. We're first going to get the value of the base pointer itself. So move %RBP into %RAX. How can we then get the offset of at which the y variable is? What can we do to RAX? Sub, right? 24 from RAX. In practice, do we use sub? No, we use add, and we subtract. We add a negative because the symbol table will store negatives already, so it's easier just to add the negatives that we already have access to. And now that we've stored in RAX the offset from the base pointer at which the y variable is at, then how can we put this result back into X? Just a move, right? Okay, let's look at another example. Let's say we want to say X equals dereferencing Y, the result of dereferencing Y. How would we do with this? Okay, so what's the first thing we need to do?
With value of y to RX.
Okay, RAX. So Y is a pointer. That means the value it stores is a what? It's an address. It's an offset. It's an address. It's an address. So that means we can dereference that address to get a value. So what we'll do, how do we dereference? Parentheses. RAX. We'll move it directly into, well, can we move it directly into? Yeah, we can't. We can only have one memory and direction operand at once in one of these instructions. So we have to move it into a temporary register first. Yeah.
Oh, okay. I was gonna say you probably move it to like RBX and then do
Exactly. RBX into -16 RBP. All right, what's the last pointer operation that we went over, that we had reviewed?
ID reference.
Yeah, so we'll say asterisk dereference assignment. So now we're dereferencing the left-hand side. So what are we going to change for this example? Let's keep the beginning part the same. We're still going to get the value out of y and put it in the A register. What do we need to do next?
you would move you do the parentheses on RX. Wait, you'd have to fill RBX first.
Okay, so RAX stores the value of y so far in this example.
Get the value of x.
This might be in a different order than what we've seen before, but the concept is still the same. Get the value of x, right? So x is a pointer, so it stores an address. So now RBX stores an address, so we can do what to it? Dereference it. So to move the value in RAX into the address at RBX, what should we put here? RAX into the result of dereferencing RBX. So again, this might be different from the order we saw before with the cogen template, but if you understand the underlying concepts, the order shouldn't really matter, as long as you understand what these are actually doing under the hood, these instructions are doing. Okay, any questions before we continue? All right. Functions in the implementation. What are the contents of the stack frame? What should the stack store? What kinds of data should the stack store? Just any answers you can think of. What should a stack frame for a function store?
Return addresses?
The return address? Actually, the return address, yeah, not the return value. Where's the return value stored? RAX. Return address is the first thing in the stack. What do we also store in the stack?
Registers.
So what registers?
RBX, specifically the base pointer.
The base
It's
pointer,
not a register.
we value the old base pointer, yeah. And the RBX register we also store. What else do we push to the stack?
Parameters,
Parameters,
if there are 6.
if there's over 6, and what's the last thing we store on the stack? What are located at runtime on a stack?
False?
Local variables. Yeah. So maybe I should show an example of this. So draw functions. Thinking maybe I should just draw another stack and walk through an example. I know, do you want to see an example of walking through a stack when a function is called? Yeah? Okay. So I'll take this here, and I'll just try and open another example of a stack that I have already ready. Okay, so before we look at the stack, let's first translate this function to simple IR. I'll focus just on the function prolog and epilogue here, so I'll remove the body of the function. I'll also include a return value, which we forgot to include earlier, but we'll return 0. It's just the return value. And I'll remove the parameters for now as well, so we can focus just on the prologue and epilogue. So what's the first instruction that we'll need to omit if we're going to correctly translate this function to assembly code? Enter function? That's the cogent function we use. What's the first part of a function in a compiled assembly code? What is the first part of a function definition? Pushing REP, and also don't forget the label. We need the label first, that's important. So main, and the first thing we do is push the old value of RBP. Then we need to do what? So that's to allocate space for local variables, but before we allocate space for the locals, what do we have to do?
You set RVP to the top.
So RSP stores what? The top of the stack, always. So we're moving RSP into RVP to get the new base pointer. What's the next variable we have to push onto the stack in order to follow the ABI? RBX. So push RBX. And now we'll pretend there's some other code here, which there isn't. One more thing I forgot. What did I forget here? What's the last part of the prologue we need to follow? What's the next thing we have to do? Yeah, allocate space for the locals. So there's only 2 local variables. Oops, 6 sub 16. There are 2 local variables. Each local variable has a size of 8 bytes, because we're dealing with a 64-bit architecture. And we're subtracting them from, what, RSP or RBP? RSP.
Do you wanna use add so that in the epilogue you can use subtract? I guess it doesn't.
Doesn't matter. Yeah. Here we're not getting an offset, so it doesn't matter. We can use sub. Okay, how do we set the return value? If we're returning 0?
Put 0 in RAX.
Yep. So move 0 into RAX. Now for the epilogue here, how do we deallocate space for add 16 to RSP? And then how do we recover the old value of RBX? Pop. And then the old value of RBP. And finally, what's the last instruction to be emit? RET. So what does RET do?
Returns the value in RAX for
Yes. Yes. Whatever, it looks at the top of the stack and will branch the flow of control to the address that's at the top of the stack. Now, so we've written all the assembly code. Let's take a look at this stack here on the right and actually see what it looks like when we step through these instructions. And I don't know if this will be enough. These will be enough stack space, but if it's not, I'll just add more as we go along. Let me create one more slot here, one more register slot here for RBX. I'll just put in 42 as an example, arbitrary value. So this will be the return address. If we're in the main function, what would this return address jump back to? Underscore start. That's the true entry point of any ELF file, executable linker file on a Linux machine. The first thing we do is push RBP. So RBP here is going to be 128. We'll assume it's just 128. That's the old value. So it goes here. RSP, I think what I'll do instead is, instead of leaving it as a register value here, I'll just put it next to where the top of the stack is, so it's easier to see. RSP was here initially. After pushing RBP, it'll be down at 56. Next, we move RSP into RBP. So what should RBP become? 56. Now we're going to push RBX. So what happens first? Yes, so RSP is going to go down to 48. And then what value is going to be put at address 48? 42. Now we're going to locate space for the local. So what's going to happen to RSP? It's going to go down twice. So 1, 2. And that effectively creates space for X and Y. So remember, if all goes well, by the time you're done subtracting space for local variables, the top of the stack should be at the same address as the last local variable. So this is correct. We should see that RSP and Y begin at the same address. This is fine because if we were to have a subsequent call to a call instruction or call another function, we would first push the return address onto the stack for that new function and decrement the stack pointer before putting it on top of the stack. So we're not going to overwrite the Y variable here. This is correct. Okay, so here we'll move the value of 0 into RAX. I'll just create another register here for showing that. We'll add 16 to RSP to deallocate the space for the local variables. So 1, 2. We'll pop the old value of RBX. It's 42 here. We didn't change it, so I'll leave it as it is, but we would take this value, put it into RBX, and then increment the stack by 8 more. Then we'd pop and restore the old value of the base pointer. 128 is here, where RSP is. So we're going to put 128 in RBP. And then because we popped, we again increment the base pointer by 8 one more time. And then finally, we have the ret instruction. That would fetch the address at the top of the stack. It would pop the stack pointer, pop that address, or go up by 8 again. So we'd be at 72 here. And we would branch the flow of control back to whatever address, instruction address, is stored in the stack here. So any questions? So you should know these steps sort of inside and out. The prologue, the epilogue, what they're doing to the stack. You should be familiar with all of that. And if you're asked to preserve any callee preserved registers, just remember that we have to keep track of RBX. I mentioned that there's other ones, don't worry about them. RBX is the only one that I'll be quizzing you on. So. How are parameters passed according to the System 5 ABI?
So first they're passed in reverse order, and in regular order. The first 6 are passed to the 6 registers are
Yeah.
and then the rest are pushed to the stack.
Yes. So the first 6 parameters are going to be pushed, well, put in registers. Are they put into these registers by the caller or the callee? The calling function or the call function? The caller, because the caller is the one that has access to the arguments that are passed to the function call. So the first 6 arguments are going to be put into registers. The remaining arguments after the first 6 are going to be pushed onto the stack in reverse order. And that's again done by the caller. And what's important to know, and you'll see this in your compiler, you might see it in some of the hard-coded functions we give you. Can't remember. Since the caller is manipulating the stack to push the 7th, 8th, and so on parameters onto the stack for the callee, after a function call, which has more than 8 arguments, you have to also deallocate those pushed parameters off of the stack as well. So keep that in mind for Code Gen 3. I think the project description tells you about that as well. How do we access variables in memory? I think we've been seeing this a lot already. What? That's how we, offsets, yeah. Yeah, we use offsets from the base pointer. Why can't we use absolute addresses to get the values of variables? Why do we have to use offsets from this base pointer register?
Not every system is going to be like that.
Not quite. Yeah.
The actual memory addresses are random.
They're random, and we just don't know them at runtime. Yeah. We don't know the actual the full addresses. We don't know the absolute addresses at runtime. So we have to use these offsets from the base pointer. How is the stack frame managed? Well, it's according to the ABI, Application Binary Interface. What is, well, I just said it, what it stands for, Application Binary Interface. What are some of the things that the ABI specifies?
You have to push the return address, you have to preserve certain registers, you have to preserve the top of the stack, be able to track that.
Yes, so the ABI specifies calling conventions more broadly. What the caller and her callee are responsible for putting onto the stack to make sure function calls succeed, and what registers the callee and caller need to preserve. The ABI specifies all of that. Prologue and epilogue, we saw that. It sets up or pushes the base pointer, pushes any preserved registers, allocates space for local variables, and then the epilogue does the opposite of all that. It undoes all those steps. It deallocates those local variables, pops the old RBX value, pops the old base pointer value. We have some pretty complete examples in the class recordings if you want to see more of those. And then, I think I already asked this, how are values returned? RX register. Okay, any questions? All right, well, that's it for the review. So if you want to go, you can. I promised a trick with macros that I'd show you, so I'll show you that. But if you have questions about the exam, interrupt me. That's more important. So, yeah. Yeah.
This is like not really a concrete question, just like, I remember you had offhandedly said that you might add extra credit
To what?
to the
I will not be, because I am offering extra credit that if, I think I already mentioned this, but if everyone completes the SPI, I don't know if it's still open, is it, the SPI? Hopefully it is. I think it closes soon, it's not already closed. But if at least 71 students, I think, complete it, then I'll give everyone one extra credit point. So far, 51 students have completed it, I just checked today. So we're fairly close. So have you not completed an SPI for this course yet? I recommend doing it, yeah?
So I know the RAX for stocks is important because it's the return value.
Yes.
Is there like is there a significance to RBX other than just like convention, it's just a secondary register to use?
As far as I know, it's just one of the registers you have to preserve, and we just use it because it's one of the general purpose registers, and B comes after A, so that's why we use it for all our examples. Yeah. I think. Let me check about the SPI when they're due. I think I put it here. Yeah, July 31st. So you all have 4 more days, I believe, to complete it. So if you haven't done it already, please do it. Your classmates will thank you. Okay, I'm going to save the recording now. That's all, everything related to this class.